So previously we've looked at how the force on a moving charge in a magnetic field can be calculated, and now we'll be going on to a more advanced application of that same formula as to how that can create circular paths for that moving charge. So let's assume we here have a uniform magnetic field and the dots are showing you that this uniform magnetic field is out of the page, and similarly the crosses would show a magnetic field into the page. So this is a uniform magnetic field which is out of the page. Let's also say that we have a particle here. So some particle, let's say this has some charge positive q, and it's moving with some velocity v into this field. So this is some velocity v, and it moves into the field with this velocity. So now what's going to happen? So again, if this is a positive charge, so I can see that the Fleming's left hand rule says that the middle finger, the second finger, should be towards the right because that's the flow of positive charge, and my field is out of the page, so my forefinger must be pointing upwards. So what I'll find is that the force exerted on this particle is going to be downwards. So then the particle inside this magnetic field would have a path like this, and then whatever velocity it had gained until this point, it's just going to move off with the same velocity outside of the field. So all of this was due to a force F which was acting on the particle. Now if you think about the origins of this force F, so we know that this force is due to the motion of the charged particle inside the magnetic field. But also if you think about the force at this point and also at all other subsequent points, we can say that this force is basically perpendicular to the direction of velocity. So force, and because by Newton's second law, whatever is the direction of the force is also the direction of the acceleration. So this is perpendicular to the velocity. Now you have seen these words someplace else as well. So whenever you have acceleration perpendicular to velocity, the idea is that in a case like this, the centripetal force, because this is going to move in an arc of a circle, so the centripetal force, which is basically the force required to keep it moving in a circle, in this case is being provided by the magnetic force which is acting on the charged particle. Right, so acceleration is perpendicular to velocity means it will move in circular motion. So it's even easier to see this circular motion in a diagram like this. So in this diagram, this shows the motion of this red particle throughout. The only thing you need to know here is that this is an electron. So if this is an electron, so whatever direction in which it is moving, I'll take the conventional current, because that's what I'll use in Fleming's left hand rule, to be in exactly the opposite direction. So for example, at a position like this, if it's moving towards the right, my second finger should be pointing towards the left, and this is the flux density into the page. So I'll have my thumb pointing outwards towards me like this. So in this case, you can see that the force is the direction of the force is perpendicular to the velocity, and that's what you'll see at all other positions of this particle as well. In each case, the force and hence the resulting acceleration is proportional to the velocity, and that centripetal force is what is going to keep it moving in a circle. So again, just following through with what we wrote above. So the centripetal force, the most used variant of that formula is mv square over r, and here it's being provided by bqv. So simplifying this, you can see that the v's will cancel out like this. Often what is needed for us is the radius of curvature, so we can write this as mv over bq. So this radius of curvature here is given by this expression. So r is that radius of the path of the circle it traces out, m is the mass of this particle here, v is the velocity with which it's moving, and again keep in mind that this is the velocity which is perpendicular to the magnetic field. And in a while we'll also talk about what happens if the v is not perpendicular to the magnetic field. B is the magnetic flux density and q is the charge. So here you are also sometimes told this, that this expression here, so here you have a thing of interest, and basically the reciprocal of m upon q, what you see here, q upon m is something called the charge to mass ratio, or more precisely the specific charge of a particle. So just in terms of proportionality, you can see here that r is proportional to m, is proportional to v, is proportional to b, is inversely proportional to b, and is inversely proportional to q as well. Now let's have a look at some of this proportionality here. So first let's talk about the effect of speed on the radius of curvature. So we just saw that the radius is proportional to the velocity. So this positively charged particle, positive q being its magnitude, is made to enter the magnetic field out of the page at 3 different speeds, v1, v2 and v3. So using Fleming's left hand rule, we can see how this would be deflected. So the field is the first finger, so that's out of the page, so that must be pointing towards you. And this one, the current is again the direction of flow of the positive charge, so your thumb would be pointing downwards. So we can see this is going to be deflected downwards. But because of the difference in speeds, you have some different paths which are created inside the field. So let's say this is some path which is v1 due to the speed v1, and this is another path due to another speed v2, and this is the third path due to another speed v3. So how can we say that which speeds are greater and which speeds are smaller? So v1 creates the largest radius, so that means it must also by proportionality have the greatest speed. So v2 creates the second largest radius, so it must have the second speed in terms of the magnitude, and v3 creates the smallest radius of curvature, so that means it has to have the smallest speed. So using this idea, I can say that here v1 must be the greatest speed, and then v3 must be the smallest speed in this order. So the greater the speed, the greater the radius, and then we can say that the amount of deflection would also accordingly be less. So we actually see something very similar to this when we work with actual particles in an instrument which is called the fine beam tube. So this is a particle which was produced in some way, and we can see that if this is its path, it's spiraling like this, with the spiral progressively getting smaller. So if the radius is getting smaller here, then that would lead us to conclude that the speed must be decreasing, if nothing else above, including m or q or b are changing, right? So if all of that is constant, then the decrease in radius must mean that the speed is also decreasing. So the particle is slowing down and it's being deflected more and more by the magnetic field. Now a very intricate idea of how the fine beam tube is constructed and how it works is not really required, but only some of it is needed just so we know how we can calculate other variables about the particle here. So in terms of the electrons, you have a path of an electron beam, and it is projected inside a low pressure gas, so you can use the light to see what kind of a path is produced. And you have two sorts of special coils which produce a uniform magnetic field inside this path, right? So between the coils you have the electrons here in the beam. So if you remember the expression we had above, which was R equals mv over bq, if we rearrange this in a way, we can say that q upon m, the specific charge, can be written as v over b r. So using this fine beam tube, we can actually find the specific charge of any particle that we have. So we would know B depending on the magnetic field, and the radius of curvature can be calculated from these tracks which are produced. So then what we really need is V here. So how do we find V? So as you can see here, the electrons will be made to move when some potential difference is applied on them. So let's say some potential difference V is applied on the particles, which causes the electrons to accelerate. So then we can use the interchange of energy to find out what would be the speed of that particle, because the electrical energy here, which is being provided to that, is really being turned into kinetic energy of the electrons as they accelerate. So what we can then say here is that the work done on the charge must be equal to the kinetic energy gained by the charge, or you can also be more specific and say by the electron. Again, it means the same thing. Just to keep it more general, I'm saying charge here. So the work done on the charge, if you remember, then voltage here is defined as W over Q. So rearranging, we can find the work done as the product of the potential difference and the charge. So if the charge here is Q, so that would become VQ, and the kinetic energy gained would be half mv square. So just rearranging this formula and making V the subject, so we get V as 2VQ over m under a square root. And then having found V from this equation, we can then plug this into the equation above here to find out the specific charge as well. So you can do this as an exercise for yourself, but when you do plug it into the equation above, you get the specific charge. So charge to mass ratio as 2V over B square R square. So using this apparatus, we can then find out the charge to mass ratio. So then if you know the charge of the particle, you can also calculate its mass. So this is how this is used practically for different particles. So we also just talked about the idea of the radius and how that provides information on the speed. The speed which provides information on the radius. So then the next one is the magnetic field. So again, just using the formula. So R was equal to mv over bq. So you can see that on the magnetic field, we can say that the radius is inversely proportional to the magnetic field. And it also makes sense when you think about it, because if the magnetic field strength is greater, it's going to pull the particle inwards more, and that's going to create a smaller radius of curvature. So using the terms we just defined here, we can also say that the radius, so basically with respect to the charge to mass ratio, or what you can also call the specific charge. So since R is proportional to m over q here, right? So R is proportional to m over q. We can also say that R is basically inversely proportional to the specific charge q over m. So the greater the specific charge, the smaller will be the radius of curvature. And again, when you think about this, this also makes sense, because if it has a greater charge, it will experience more deflection, and hence it would be curved more, leading to a smaller radius. So let's see this using a practical example. Let's say we have an electron versus a proton. So for electrons and versus protons. So for electrons, we know that the charge is 1.6 into 10 to the negative 19 coulomb, and the mass is 9.11 into 10 to the negative 31 kg. So then the charge to mass ratio, Q over m, turns out to be 1.76 into 10 to the 11, obviously coulomb per kg. And if we do the same analysis for a proton here, So a proton has charge the same, only positive. So 1.6 into 10 to the negative 19. But we know a proton is much heavier. So it's 1.67 into 10 to the negative 27 kgs. So the charge to mass for this one, when you work it out, that turns out to be 9.6 into 10 to the 6 kg. Sorry, not kg, coulomb per kg. So then how do you think their radius would be in a magnetic field? So again, let's say you have a uniform magnetic field which is out of the page, and let's see how their behavior is in this sort of a field. So let's say you have both the particles entering the field like this. So this is the electron, and the one in purple is the proton. Right? So for the electron here, if we use the Fleming's left hand rule to find out which direction it's going to go in. So I know that the field is out of the page, so the index finger must be pointing at me. But since this is an electron, the second finger must point opposite to the direction of where it's going, because that's going to be the direction of conventional current. So what we'll find is that the electron is going to curve upwards, right? And again, we can see here that this charge to mass ratio is much larger. So if it has a larger charge to mass ratio, a larger specific charge, this means its radius is going to be smaller. So this is how the electron is going to go in the magnetic field. As opposed to this, if we look at the proton, so the proton, again, the first finger would be pointing outwards at me, and the second finger would be pointing towards the right. So the force would be downwards. But because this has a much lower charge to mass ratio, the radius of this particle would be much larger. So something along these lines is how the motion would be. And again, needless to say, if you have something like a neutron here, so because of having no charge and essentially no charge to mass ratio, it would just go straight through. So this would be the path for a neutron. So just one last point which is worth mentioning here is that throughout all of our conversation leading up to this point, we have assumed that the velocity is just perpendicular to the magnetic field. But what if that isn't the case? So what if the magnetic field strength is in a direction like this and the particle moves in a direction like this, so that it makes some angle theta? So let's say this angle. So if this is the velocity v and it makes an angle theta with the magnetic field lines, so you know we can resolve these into two components. So this component along this direction would be the cos component, and this one here, this would be the sine component. So here the sine component is what is actually perpendicular to the magnetic field line, which makes it move in a circle. But you also have the v cos theta component, which is going to take it forward in this direction. So the resulting path then is something like this. So you're also tracing out circles, but simultaneously you're also moving out forward. So that leads to a helical path. And this happens if particle enters field with a velocity parallel to the field, right? So if it's not just moving perpendicularly, if it's also has some component which is parallel to the field, so it will then have a helical path inside the field. So in the next video, we'll also see an example of this.